Hi, this video investigates sums of integers. For example, the sum of the first n integers or the first and odd integers. We can also add the squares of the first n integers or their cubes. Sums like these were studied for thousands of years and they are connected by a surprising pattern. In this video, we will reveal an elegant proof of this pattern hidden within Pascal's triangle. Let's first look at the aforementioned examples. The well-known arithmetic series sums the integers 1 to n. It is equal to half times n plus 1. To show this, we employ a trick discovered by Gauss as a schoolboy when he was given the task to sum 1 to 100. We take two copies of these numbers and group them into pairs. 1 is grouped with n, 2 is grouped with n minus 1, and so on. We end up with n pairs of numbers, each adding to n plus 1. So in total, they add up to n times n plus 1. To get the sum of 1 to n, we have to divide this by 2, since we started with two copies of 1 to n. Next, let's investigate the second example. The first and odd integers add up to n squared. To prove this, we draw a picture again. A square of size n squared can be divided into L shapes of sizes 1, 3, 5, and so on. So the sum of the first and odd integers has to be equal to n squared. In another example, squares of the first n integers are added. Their sum is equal to a cubic polynomial in n. These are so-called pyramidal numbers, since they describe the total number of balls in a pyramid of height n. They were first understood by Archimedes more than 2000 years ago. For a picture proof, suppose that we fill a triangle like this. The kth row contains k times the number k. The total sum of all numbers within the triangle is equal to the unknown pyramidal number. We construct two other copies of this triangle, rotated by 120 degrees and minus 120 degrees. By adding these three triangles together, we end up with a triangle having 2n plus 1 everywhere. And this triangle contains 1 plus 2 plus up to n of these numbers, which we already know is equal to half times n plus 1. The resulting sum has to be divided by 3, since we started with 3 copies of the triangle. In total, we get the value n times n plus 1 times 2n plus 1 divided by 6. As the last example, consider adding cubes of the first n integers. Their sum is equal to a quartic polynomial in n. In particular, it is equal to the square of the sum of 1 to n. This was already known to Nicomachus in ancient Greece. One picture proof cuts cubes of sizes 1 to n into pieces and arranges them into a square of the side equal to the arithmetic series 1 to n. Another proof hides within the multiplication table n by n, first described by Rose in 1893. If we sum the table by columns, the first column is the arithmetic series 1 to n. The second column is the same sum multiplied by 2, the third one is multiplied by 3, and so on. In total, we have the arithmetic series 1 to n multiplied by itself. On the other hand, one may draw the same L shapes as in the case of the sum of the first and odd integers. The values in these L shapes add up to 1 cubed, 2 cubed, and so on, which you can check as an exercise. Nicomachus's identity is thus established. While all these proofs are beautiful, they are all different and very ad hoc. It is not clear how to modify them for other sums of integers. One mathematical principle is to look for a more general pattern. If we are lucky, this general pattern might be much simpler. Counterintuitively, the proof of a more general statement might be easier. This is the power of mathematical abstraction. Looking at these four identities, the left-hand side is a sum of a polynomial p in K. Its degree d is shown on the left. Ignoring the particular coefficients on the right, we get another polynomial q in n. Further, its degree is precisely 1 larger than the degree of p. So the sum of a linear polynomial becomes a quadratic polynomial, the sum of a quadratic polynomial becomes a cubic one, and so on. The general statement says that for an arbitrary polynomial p of degree d, when summing p1 plus p2 plus up to pn, the result is qn for another polynomial q of degree d plus 1. We will call this property by saying that p sums to q. An elegant proof of the general statement, hidden within Pascal's triangle, will be revealed in this video. Before proving it, let's discuss how the general statement can be applied. Suppose that we are given a polynomial p, for example k squared. We want to determine coefficients of the unknown polynomial q. For k squared, the general statement implies that q is a cubic polynomial. We want to find out its unknown coefficients a, b, c, and d. A key property of a polynomial of degree d is that it is uniquely determined by any d plus 1 values. In the case of our cubic polynomial, we just need to know 4 values. These can be found by computing the sum of k squared for the first 4 values of n depicted in the table below. For each value of n, when plugged into the polynomial, it has to be equal to the value of the sum. We get a system of 4 linear equations with unknowns a, b, c, and d. When rewritten into a matrix, Gauss-Jordan elimination can be applied to solve this system. First, it eliminates all non-zeros below the diagonal by subtracting rows with pivots. Next, it zeroes out everything above the diagonal. We end up with the identity matrix, and the solution is found in the right-hand side. The system is solved by a equal 1/3, b equal 1/2, c equal 1/6, and d equals 0, which gives precisely the same cubic polynomial as we obtained from the picture proof presented in the beginning of this video. Let's discuss how to prove the general statement. We will proceed in 2 steps. First, we will show that it is sufficient to prove it only for some polynomials p, and the result can be easily expanded to the remaining polynomials p. Then, we will find suitable polynomials p, for which it will be easy to prove that their sums are equal to some polynomials q. Suppose that we know that a polynomial p sums to q, and another polynomial p prime sums to q prime. It easily follows that p plus p prime sums to q plus q prime. Similarly, when p sums to q, any multiple c times p sums to the multiple c times q. These 2 properties are called linearity. Let's apply linearity to derive the formula for the sum of the first and odd numbers we have seen before. It is the sum of the polynomial 2k minus 1. We already know the sum of k, which is the arithmetic series, and the sum of n ones is obviously equal to n. By combining these together using linearity, the sum of 2k minus 1 is n squared, which gives the same result as the picture proof in the beginning of this video. Similarly, one can derive a formula for general arithmetic series, which is the sum of a polynomial a times k plus b. Linearity of polynomial sums is very powerful. We already know that the general statement holds for 1, k, k squared, and k cubed. Linearity implies that it holds for all cubic polynomials p, and if we can prove it also for k to 4, k to 5, and all higher powers of k, it would hold for all polynomials p. Unfortunately, that is not so easy to prove, and it is known in the literature as 1ᵏ+2ᵏ formula. The resulting coefficients in Q are quite complicated, and the full proof was derived by Jacobi only 200 years ago. The standard proof presented on Wikipedia uses exponential generating functions. An unknown sequence is encoded into a function, for which results from calculus can be applied and equations can be solved. If we use this technique right, the values of this unknown sequence may get revealed. Actually, only the first part of this proof is displayed. The second one is here. While generating functions are powerful and useful to know, needless to say that this technique is not easy or elementary. Therefore, this video chooses a different approach. The key idea is that we do not necessarily need to prove the statement for p equal k to 4. Any polynomial of degree 4 is sufficient. For example, suppose that we could show that this polynomial of degree 4 sums to some polynomial q of degree 5. We already know that k squared sums to this cubic polynomial denoted q2, and k sums to this quadratic polynomial denoted q1. Linearity implies that k24 sums to some other polynomial of degree 5. So we are done with the first half of the proof. Suppose that we can prove for every degree d that some polynomial p of degree d sums to another polynomial q of degree d plus 1. Linearity then implies that the statement holds for all polynomials p. If you know a little bit of linear algebra, one just needs to prove the statement for a basis of polynomials, and linearity takes care of the rest. In the remainder of this video, we will show that these suitable polynomials p are hidden within Pascal's triangle. Pascal's triangle is an infinite triangle of numbers. On the outside, all the numbers are equal to 1. Interior numbers are obtained by summing the two numbers above them. So 1 plus 1 becomes 2, 1 plus 2 is 3, 1 plus 3 is equal to 4, 3 plus 3 gives 6, and so on. The resulting object has many magical properties, and we will show some of them. Even if you are familiar with Pascal's triangle, we will present it in a way which might be new to you. Notice that there are blue and red arrows between numbers, which are usually not shown when drawing Pascal's triangle. Blue arrows always go one down to the left, while red arrows always go one down to the right. It turns out that each number of the triangle represents the count of different paths using blue and red arrows, going from the top number to this number. For example, there are 10 different paths leading to the highlighted number 10 from the top. So Pascal's triangle describes the counts of paths within an infinite grid, only going in two directions. Let's prove that this interpretation of Pascal's triangle is correct. For the top number, there is exactly one path of length 0 ending in it. For the other outer numbers, there is only a single path either consisting of only blue arrows or only red arrows. For an interior number, each path leading into it either ends with a red arrow or with a blue arrow. For the number 10, there are 10 paths in total ending in it. 4 of them end with the red arrow going through the number 4, and 6 of them end with the blue arrow going through the number 6. So the total number of paths ending in 10 is the sum of the total number of paths ending in 4 and 6. Counts of paths are added in the same way as numbers in Pascal's triangle, which proves by induction that they are identical. We introduce the coordinate system for Pascal's triangle to be able to describe its numbers directly. The lines are numbered from top, starting with 0, and we denote the line number by n. The diagonals are numbered from top left, again starting with 0. The diagonal number is k. Whenever a blue arrow is used, the coordinate n is increased by 1 while k is left unchanged, and a red arrow increases both coordinates n and k by 1. The number at coordinates n and k is called n⁴k and denoted by writing n on top of k in parentheses. For example, 5⁴2 is equal to 10. Let's now derive how to compute the value of n⁴k directly without summing Pascal's triangle from top. This procedure will explain why numbers in Pascal's triangle are called n⁴k. Since n⁴k belongs to the end line of the triangle, each path ending in it consists of exactly n steps. Further, it uses precisely k red arrows and n-k blue arrows. For example, in the case of 5⁴2, each path has 5 slots into which arrows are placed. We first choose positions of 2 red arrows. There are 5 possibilities where the first red arrow can be placed, and then 4 possibilities remain for the other red arrow. When red arrows are placed, the positions of the remaining 3 blue arrows are fully determined. This gives 20 different paths ending in 5⁴2. Unfortunately, the argument cannot be fully correct, since we already know that there are just 10 different paths ending there. The issue is that the precise order in which red arrows are placed does not matter. If we place them in the opposite order, we still get the same path. So each path is counted twice, and we have to divide the number 20 by 2, which gives the correct count of 10 different paths. In general, the formula for n⁴k selects positions of k red arrows, for which we have n times n-1 times down to n-k+1 possibilities. The remaining positions are taken by blue arrows. The precise order in which positions of red arrows are chosen does not matter. Thus, we have to divide the resulting sum by k times k-1 times down to 1, since red arrows can be placed in an arbitrary order. This product in the denominator is called k factorial, and it is denoted by k with the exclamation mark. The described procedure nicely explains why the value is called n⁴k, since it chooses k positions out of n slots. This formula reveals one essential property. Suppose that k is fixed, but the value of n changes. The denominator k factorial becomes a constant. The resulting formula is a polynomial in n of degree k. This is needed to link Pascal's triangle to polynomials and their sums presented in the first half of this video. In summary, we have introduced Pascal's triangle as an infinite triangle of numbers. we have explained that these numbers encode counts of paths in a grid, and we have derived a formula to compute any number n choose k, and this formula is a polynomial in n of degree k. Pascal's triangle hides many beautiful patterns, and I want to show you a few of them. Since we know that each number describes counts of paths ending in it, we can use this knowledge to quickly prove most of these patterns. First, the entire triangle is symmetrical about the vertical axis. N choose k is equal to n choose n minus k. For every path ending in n choose k, suppose that we swap red and blue arrows. The path gets reflected about the vertical axis, ending up in n choose n minus k. Therefore, paths ending in n choose k and ending in n choose n minus k are paired by the reflection, so their counts are the same. Another pattern states that sum of all numbers in the nth row is 2 to n. The sum of these numbers is equal to the total number of all paths of length n. We have two possibilities for the first arrow, since we can choose either a red arrow or a blue arrow. Similarly, there are two possibilities for the second one, third one, and so on. In total, there are 2 to n different paths of length n. Suppose that instead every other number of arrows is added up. Their sum is always 2 to n minus 1, so the numbers at odd indexes and the numbers at even indexes add up to the same value. We already know that there are 2 to n minus 1 paths ending in the row above. Each of these paths can be extended in precisely one way to end up in n choose k, where k is either even or odd, so the number of paths ending there is also 2 to n minus 1. The next pattern states that squares of numbers in the nth row add up to 2n choose n. The reason is that every path ending in 2n choose n has to cross the nth row at some point n choose k. We know that there are n choose k paths starting in the top and ending in n choose k. And by the symmetry, there are also n choose k paths starting in n choose k and ending in 2n choose n. Since we can glue any pair of these paths, the total number of paths going from the top towards 2n choose n while passing through n choose k is n choose k squared. To get all paths from the top ending in 2n choose n, we have to sum this over all values of k. So the sum of squares of the nth row is 2n choose n. Pascal's triangle also hides Fibonacci numbers. We just need to sum these highlighted diagonals. Fibonacci numbers start with 1 and 1. Each next Fibonacci number is obtained by adding the two previous ones. So the first few Fibonacci numbers are 1, 1, 2, 3, 5, 8 and 13. And they are found within Pascal's triangle. To see that this works, consider two consecutive diagonals. All red arrows from the top one and all blue arrows from the bottom one lead to the next diagonal below them. Each path ending in these two consecutive diagonals can be extended in precisely one way to end up in the next diagonal. So the sum of two consecutive diagonals has to be equal to the sum of the next diagonal. For the last pattern, we need to draw a larger part of Pascal's triangle. When all odd numbers are highlighted, the resulting pattern is far from random. It is nicely symmetrical and repetitive. In fact, it is a Sierpinski triangle, which is a fractal pattern constructed as follows. It starts with a triangle from which the middle triangle is removed. Then the middle triangles from the remaining 3 triangles are removed, and so on. In Pascal's triangle, we currently see the third iteration, where 1 + 3 + 9 triangles are removed. When zooming out to include more numbers of Pascal's triangle, the pattern would repeat and further iterations would be visible. As an exercise, you can try to explain why this pattern appears in Pascal's triangle. We have seen several beautiful patterns of Pascal's triangle. Well, it is a truly magical mathematical object. Further, we presented elegant proofs of these patterns using numbers of paths. And there is one more pattern which we need to investigate to prove the main statement of this video about polynomial sums. This pattern sums the first few values of a diagonal in Pascal's triangle. It is equal to the highlighted number below. This is the so-called hockey stick identity, since the numbers form a hockey stick. The green numbers form a shaft, while the purple sum is its toe. To prove this, consider all paths ending in the highlighted purple number. Each path has to cross the purple line at some point. After crossing, the rest of the path consists of all blue arrows, so it is uniquely determined. Therefore, the number of paths which are crossing at one particular point is equal to the green number it goes through right before crossing the purple line. The total number of paths ending in the purple number is obtained by summing counts of all paths ending in all green numbers. Hockey stick identity is the following formula for the sum of the first n values of a diagonal D. It states that it is equal to n + 1 choose D + 1. Notice that the sum starts at k = D, but we can easily modify it to start at k = 1, since the values k choose D are 0 anyway when k is smaller than D. The reason is that it is not possible to choose D positions out of k slots when k is smaller than D. In other words, the numbers outside of Pascal's triangle are zeros. Hockey stick identity is essential for this video. It states precisely what we needed to prove the general statement about polynomial sums. The sum of k choose D is a sum of a polynomial p of degree D, and it is equal to n + 1 choose D + 1, which is a polynomial q of degree D + 1. So we have found some polynomials p for which the statement holds. Actually, hockey stick identity implies for every degree D that there exists some polynomial p of degree D whose sum is equal to another polynomial q of degree D + 1. By linearity, the same holds for every polynomial p. The proof of the general statement is now done. Let's conclude this video by looking at the case D = 4. Hockey stick identity states that the sum of k choose 4 is equal to n + 1 choose 5. By plugging in the formulas, we get that the sum of this polynomial p of degree 4 is equal to this polynomial q of degree 5. The coefficients are not super nice, but it does not really matter. We just needed to establish this equality for any polynomial p of degree 4. We can use it to derive the formula for the sum of k to 4. We simplify a little bit and move everything except the sum of k to 4 to the other side of the equation. We already know formulas for the sums of 6k cubed, 11k squared, and 6k. By plugging them in, we get that the sum of k to 4 is the following polynomial of degree 5. We have just correctly derived one of 1ᵏ+2ᵏ's formulas. This nicely verifies that hockey stick identity works correctly. This presentation is created in the web application OrgPad. You can find a link to it in the video description. I am one of the creators of OrgPad, and it is a great tool for building better understanding and solving problems, no matter how hard and complex they are. If you want to see more videos like this one, you can help by checking OrgPad out and supporting our work. Use the promo code polynomials to save 20%. Also, you can check another video I made about complex numbers and why they are not imaginary. In summary, we have seen several beautiful identities involving sums of natural numbers and their powers. We have presented picture proofs for them. Then we noticed a general pattern which was much simpler and easier to prove. And we have constructed an elegant proof using linearity and holistic identity. Further, we have explored the beauty of Pascal's triangle, which is one of my favorite mathematical objects. I hope you have learned something new, and thank you so much for watching. If you have any questions, let me know in the comments. And please like this video and subscribe.